How's it going? My name is Patrick, and I'm going to be presenting my acrobot project. So what is the purpose of this project? We're just going to be trying to teach a two-dimensional acrobat to swing to a certain height using cue learning. How does the model work? So this is going to be implementing reinforcement learning, specifically cue learning. What cue learning is we have a table that's usually instantiated with all zeros in it. That maps to a certain action the agent can do, in this case the agent being the acrobot. And it's going to be feeding it observations from the environment. Maybe the thing is going at a certain speed at a certain position, and it performs an action in that position, and if that action is beneficial to the agent, it'll keep it, and if not, then it won't. So it eventually builds up this great big table of actions for any given observation. So in the model itself, all the activation functions are going to be linear in shape. So we're either going to just be doing linear or ReLU. ReLU for most of the hidden layers. I found that hyperbolic tangent and sigmoid squishes the results, and it doesn't really train properly with it. Mean squared error is the loss function, and atom is the optimizer. So the approach. All this is coded in Python and uses TensorFlow and Keras backends. This, as I said before, was is an implementation of an environment that OpenAI Gym provides called Acrobat version 1. So this environment was basically made with reinforcement learning in mind. So the best option was cue learning because that was just the nature of the environment. It gives good observations, and the agent really doesn't have too complex of actions. You can either move the thing to the or push it with a constant force to the left, or push it to a constant force to the right, or just not do anything at all with it. Also, over here, you notice that the learning rate is a constant alpha here. I changed that to a function of the score. So that's analogous to almost neuroplasticity and crystallized intelligence. So when you're a baby, you tend to learn more quickly. And as you age, you realize what things work and what things don't. And your brain slowly loses that plasticity, and it becomes crystallized. So that's almost like its analog. So we made it so that this learning rate is a lot higher when it first starts out. So it's able to take these big jumps and big risks while learning, and it'll be very beneficial in the beginning. But as the score increases, we don't want this thing to just change its whole entire philosophy about how to move this thing. So we don't want it to have a large learning rate in the end. We want it to be a lot smaller, so it just tweaks it. So the real world applications. So the first is biomechanics. This thing can show people how to really move, especially gymnasts that need a good visual on how to keep their momentum going so they can swing around the bar well. This can transport items into higher locations and visualize chaos theory. So as you'll notice, the thing has two joints, and it's almost a double pendulum, and you can see it while it's training that when it tweaks something very minor, sometimes it actually really throws off the entire thing, and it shows that small actions can really impact something like this, and impact the system in a great way. Great as in large, not necessarily for the better sometimes, but the learning can be a little inconsistent that way because it's just the nature of the thing is chaotic. So other real-world applications. So when we generalize this to reinforcement models in general, self-driving cars, assembly line machines use this, endless applications in robotics. I mean, robots are the agent. The real world is the environment. It's a recipe for this type of learning. So a lot of robotics use reinforcement learning. Okay, so I'm gonna just cut to the demonstration portion of this, and I'll see you when it's done. How's it going? So this is the demonstration of my acrobot project. This uses openai to get this environment. So the agent has 3 movement options. One is to have a constant force to the right. The second is no force, and the last one is a force to the left. They're all being applied to the middle of the robot, and you can see it bend in the videos. So here's where the model is instantiated. Here are the methods that do all the training and update the Q tables. There are 2 ways to train this thing. You can either train it until it reaches the height that you want it to in a certain amount of time, or you can just do it with a set amount of episodes you want it to train. So here is the method that trains it, and we'll be back when this thing is almost fully trained. So here's the model now. It's getting pretty good at getting up to that height. It just tries to build up its momentum until it can finally launch itself up there. Here are my citations. Thank you for your time. Okay, now that you saw the model in action, what can be improved? So the physics environment isn't necessarily analogous to the real world. It does not do things like air resistance justice, or very small things like friction. And like I said before, small things can really throw this thing off. So the base, if you want to implement this thing in the real world, it would be good to train in the environment, and then afterwards get the model used to the real world, because they're not super analogous to one another. So the learning process, like I said before, is a little inconsistent, and the way that the thing learns is it only gets a score if it can get up that high. So there's a little bit of, it starts off pretty slow because it doesn't necessarily know what the score is, how to get this score, until it finally realizes, oh, if I swing up here, I get a score. So better sub goals could be made. Like maybe if we started the bar a little lower, then made it higher incrementally, so that it knows, okay, the higher I go, the better my score will be. And then after it reaches its max height, change it so that the score is dependent on the time. So the faster it gets up there, the better the model does, the more it gets rewarded. Here are my resources, so thank you.